Hello, Integrated Math 1, and welcome. Okay, I can do this. Module 1, Topic 1, Lesson 3. But Lesson 3 is going to go, it's a longer one, so we're not going to be able to do it all in one video. I know you're sad and disappointed. So we're going to call this Lesson 3 Part A, Day 1, whatever works for you. But you get the idea. So here we are doing functions and non-functions, and we're going to be playing with all kinds of things. So before we get too far into things, first of all, let's just talk for a second. We keep mentioning quantities and relationships and all that kind of stuff. Can we actually talk about what we mean when we say a relation? So a relation, pardon me, having some issues. Oh my goodness, sorry. Wow. So a relation is what we refer to as the mapping between a set of input values called the domain and a set of output values called our range. All right. So when we're talking about a relation, we're just saying, hey, how do we get from our domain to our range? How do we get from our input to our output? And that's all we're talking about. Now you can represent this several different ways. We are on page M141 in your book, if you're not sure where we wandered off to. Oops, sorry, I'm already getting a little too carried away here. So the deal is you can use ordered pairs to describe a relation, right? It's just a set of points. We could just list off the points, right? -2, 2, 0, 2, 3, -4, 3, 5. You can just list off a set of points to explain the relation. When I plug in this is what I get out of it. Yay. Another way that you can express a relation is by using an equation, right? Y equals 2/3 x minus 1. I plug in for x and I get a 1 out of it. So my input, my output, my domain, my range, all that good stuff. You can do it verbally, right? You can just say, hey, what's the relation between students in your school and each student's birthday? You can just use your words to describe it. Use your words. It works fine. And then, of course, there's this thing we call mapping, and that is where in one circle you have all of your domain objects, and then in another circle you have, or oval, I guess, you have all of your range objects, and so you draw arrows. When I plug in a 1, this is what I get. When I plug in a 4, this is what I get. When I plug in a 2, this is what I get. So my inputs and my outputs are all still being represented here. And, of course, the last ones, and that is a graph, right? I can represent a relation by showing a graph. When I plug in a 4, I get an answer of 2, right? I can just do it on a graph. That's fine. And last but not least, on a table, if I plug in a -1, I get a 1, right? If I plug in my domain, what do I get for my range? So tables work great for that as well. So along those lines, what I would like you to do is start thinking about function. Now, we've said a function is a relation that assigns to each element of the domain exactly one element of the range. So when I plug something in, I only get one thing out. Each element of the domain gets exactly one element of the range. If I plug something in, only one thing comes out of it. And so again, we can express functions in a number of ways. Like we were just showing all those relations, we can do that. So here's what I would like you to do. On page M142, I would like you to analyze these relations. I've got a whole bunch of these for you. So analyze the relation represented as a table. So here we have a relation, it's a table, and I want you to tell me, is the relation a function? Go ahead and hit pause and jot down your thoughts on that, and then hit play when you're ready to check your work. So let's see what we got here. Yeah, each element in the domain has exactly one element in the range. Check it out. If I plug in a -1, all I get is a 1. If I plug in 2, all I get is 0. Plug in 5, all I get is -5. Plug in a 6, all I get is -5. If I plug in a 7, all I get is -8. Now notice, the domain, there's no repeaters in the domain. It's okay, though, if 2 items in the domain get the same answer in the range, just so long as if I plug in a 5, I only get one answer. And if I plug in a 6, I only get one answer. I only get one output, then we're a function and we're doing okay. So I got a few more of these for you, as you can see. What about our mapping? Again, hit pause, jot down your thoughts. Is this relation a function? and then hit play when you're ready to check your work. So I'm noticing, okay, if I plug in a 1, I get a 2. If I plug in a 2, I get 0. But when I plug in a 4, I get 2 answers. I get 5 and -5. So this tells me this relation is not a function. I have an element in my domain that maps onto more than one element in the range. When I plug in a 4, I don't get exactly one answer. I get 2 answers. And that's no bueno, no good. What about this one? The relation between students in your school and each student's birthday. Hit pause, jot down your thoughts, hit play when you're ready to continue the discussion. All right. So I don't know what your thoughts were, but my thoughts were this: relation between students in your school and each student's birthday. I'm pretty sure that each students are my input, which means birthdays are my output, which means each student only has one output because I'm pretty sure we only get one birthday. Yeah. Each student has one and only one birthday. That's how it goes. It's life. Don't get me wrong. I know friends that celebrate birthday month. I know people that celebrate their half birthday, but you only get one actual birthday. Just saying. It's a thing. So we talked about how you can also represent relations as equations, right? So you can also write an equation representing a function using what we call function notation. So let's look at that relationship between an equation and function notation. So consider this scenario. We have this company here, which we're going to call US Shirts. US Shirts charges $8 per shirt plus a one-time charge of $15 to set up a t-shirt design, right? Takes time, money, all that to actually set up the design. So $15 to set it up, no matter how many shirts you buy, and then another $8 per shirt after that. So we can write this lovely equation here. Y equals 8x plus 15, right? Here's our $15, right? No matter how many shirts we get, and then 8 times however many shirts we get, because it's 8 per shirt. So this equation, y equals 8x plus 15, can be written to model this situation. The independent variable x represents the number of shirts we're ordering, right? That's my input. How many shirts am I ordering here? It's my independent variable. It's what comes first. And the dependent variable y represents the total cost of the order in dollars. The cost depends on how many t-shirts I'm buying, right? So y is going to be my dependent variable. Now you're used to equations written like this. Y equals 8x plus 15. That's not new. But we can rewrite this equation if we're like, hey, this is a function. We can rewrite it using function notation. We are on page M143 if you're not sure where we went away to. And you'll see this on your page there down in the corner. Function notation is just a way of representing functions algebraically. So it's still going to look a lot like our equation, but there's going to be a little difference. Function notation usually looks something like this: f and f parenthesis x parenthesis, but we read it as f of x. Okay, so the function notation f of x is read as f of x and indicates that x is the independent variable. So this is why function notation is kind of cool. This little f of x guy, I mean, we usually use f for, function. And x tells me, hey, that's my independent variable. And so the way we could rewrite that equation that we just did, that y equals 8x plus 15, is we can rewrite it as f of x equals 8x plus 15, where x is my independent variable, so that's where it goes right in there. And then f just says, hey, this is the name of my function, right? This is a function, by the way, this whole t-shirt thing, right? Because for each number of t-shirts ordered, my independent value, there's exactly one total cost dependent value, right? If I order 10 t-shirts, that's how much I pay. There's not a bunch of different prices that I'm going to pay when I get the 10 t-shirts. This is the price I'm going to pay. So because the relationship is a function, we can rewrite y equals 8x plus 15 in function notation. We write it like this. F of x equals 8x plus 15. So f is the name of my function, and this whole f of x tells me that x is my independent variable. X is my input. So the cost defined by f is a function of x, right? Defined as the number of shirts ordered. So x is the number of shirts I'm ordering. F is the cost of all of those shirts that I'm ordering, which is a function of x, a function of the number of shirts I'm ordering. By the way, you don't have to use f and you don't have to use x. You can write a function a lot of different ways. For example, instead of f of x equals 8x plus 15, I could write this function, this whole t-shirt cost function. I could write the t-shirt cost function as C of S equals 8S plus 15, where the cost, defined as C, right? C would be my cost, is a function of S, which is the number of shirts that I'm ordering. Now, I admit I don't usually like to use S for my variable, but hey, we're gonna make it work, all right? That's fine. So considering our lovely little function here, C of S equals 8S plus 15, I would like you to answer 2 questions for me on number 4. What expression in the function equation represents A, the domain of the function, and B, the range of the function? Remember we said A was input, and domain was input, and range was output. So with that in mind, go ahead and answer parts A and B on question number 4. Hit pause to do that and hit play when you're ready to check your work. So if my domain is my input, then that means S is my input, right? S is my independent variable, my input, all that stuff. So I would say that the expression S represents the domain of my function because domain is my input. S is my input. The number of shirts is my input. For the range of the function, I would have to say that C of S is my range because that's dependent on S, right? You could have said C of S. I guess if you really wanted to, the other option is you could have told me that 8S plus 15 represents the range of my function. I mean, that would also be possible. But here's where I want us to get really fun. I want you, instead of just giving me variables, give me like numbers. Describe the possible domain and range for this situation. What are the possibilities for my input and what are the possible numbers I would get for my output? Go ahead and hit pause and put down your thoughts. Hit play when you're ready to continue the discussion. So we said domain was S, and we said that S was my domain value, and we said that S was the number of t-shirts I ordered. And I'm like, well, you either order a t-shirt or you don't, right? There's not going to be like 3.5 t-shirts. Like, you're not going to order half a t-shirt. That's not how it works. You either get the t-shirt or you don't get the t-shirt. The other thing is you're not going to order negative t-shirts. Again, I don't know how that would work. So that tells me I probably wouldn't even order 0 t-shirts, right? Because if I were ordering 0 t-shirts, why am I calling these people and bothering them? So that means the possibilities for my input, my possibilities for my domain for my t-shirts would be like 1, 2, 3, 4, 5, 6, 7, 8, on and on and on and on and on, forever and ever. So I'm going to say that my domain is the set of whole numbers. Don't want the integers because I don't want the negative guys. So I'm just going to say it's a set of whole numbers. And I'll say whole numbers. I'm going to leave 0 with that. I guess I could order 0 t-shirts and pay them $15 to set it up and not get a t-shirt. That feels weird, but you could. What about our range? All right, so the range is my cost. Well, the range isn't going to be negative, and the range isn't going to be 0. And the range really depends on how many t-shirts I'm ordering. So I give kind of a weird explanation, but it works. All right, just go with it. So the range is the corresponding set of whole numbers, so still whole numbers, that result from substituting values into the expression of 8s plus 15. So my range is going to be the whole numbers I get when I plug in stuff for S, and that's going to be my range. Yay. One of my favorite ways to know whether or not a function is a function, whether or not a relation is a function, phrase that again, is to look at the graph. There is a visual way to know whether or not a function on a graph, whether or not a relation on a graph is a function. And it's really easy. It's called the vertical line test, and just basically means vertical line test is a visual method to determine whether a relation represented as a graph is a function. And to apply the vertical line test, consider all of the vertical lines that could be drawn on the graph of a relation. So you could draw a vertical line here or here or here or here. Please remember vertical line means straight up and down. Thank you. So anywhere that I draw a vertical line, it should only intersect your graph once. If any of the vertical lines, so I drew a vertical line, if any of the vertical lines intersect the graph of the relation at more than 1 point, the relation is not a function. So you can see this first guy, anywhere that I draw a vertical line, it's only going to intersect my graph once. So this graph is a function. But if we look at this guy over here, I have a little issue, right? Because if I draw a vertical line, it actually intersects my graph twice. So it's not a function. Boo, it failed the vertical line test. Keep in mind that the vertical line test applies for both discrete and continuous graphs. And just to remind ourselves, a continuous graph is like those smooth lines or smooth curves, right? You can put your pencil down and follow it and never pick the pencil up. That's a continuous graph, and that's what we're would be continuous graphs, right? I can put my pencil here and follow it, put my pencil here and follow it. A discrete graph is when we have isolated points. So they're not connected. It's just a bunch of little points, but you can see a pattern happening. So the vertical line test applies for both discrete and continuous graphs, whether you have a bunch of points or whether you have a line. That vertical line that you draw should only ever intersect once, never more. So how can you determine if a relation as a set of ordered pairs is a function? I'm going to give you a moment to think about that. Write down your thoughts, hit pause, and then hit play when you're ready to check. See how you're doing. So I have a tendency to look at those x coordinates. I'm not going to lie. I look at the x coordinates, okay? A set of ordered pairs represents a function if each x value or x coordinate in your ordered pairs maps to exactly one y value. That when I plug in that x value, I should only get one y value out of it. What about if you're dealing with an equation? Give this one a little bit of thought. How can you determine if a relation represented as an equation is a function? Go ahead and hit pause, jot down your thoughts, and then hit play when you're ready to check. So my thought on this was, if I can get that y alone on one side of the equation, generally, I'm probably going to be okay. We call that solving for y, right? So an equation represents a function when you can solve for y. And that means you can only get one y value for any given x value. Again, if I plug in for x, I should only get one answer out for y. So that's why I like it to be a y equals, get that y alone kind of thing. Usually if I can do that, I'm feeling pretty good that it's a function. There are exceptions, but generally that's how it works. So with this in mind, question number 8 over on page M145. Question number 8 has a whole bunch of these. I just have part A up on the screen, and I think you have like A through F. So now that we've talked about all the different ways to represent a relation, we've talked about how to know whether all of those different relations are functions. Here's what I would like you to do. I would like you to go through all of number 8, A through F, and determine which relations represent functions. So tell me, yes, it's a function. No, it's not a function. But there's a bonus. If the relation is not a function, state why not. Tell me why not. Go ahead and hit pause and work your way on number A through F. And then hit play when you're ready to check your work. Are you ready? So is this bad boy a function? Well, if I plug in a 1, 3 to the 1 power is 3. I only got one answer. If I plug in a 2, 3 to the 2nd power is 9. Still only get one answer, and that would keep going and keep going, no matter what I plug in for x. I do notice that my y is alone, so I'm feeling pretty confident with that y equals. That this relation is a function. Oh, yeah. All right. What about part B? For every house, there is one and only one street address. Is that a function? Yeah, I'm going to say it is. So I'm going to say this relation is a function because, yeah, your home only has one address. If your home had more than one address, I'm afraid the postman would be very confused. Your Amazon packages would never find their way to you. Just saying. Here we go. I got a table. Is this relation a function? I'm going to say no, it's not a function. This relation is not a function because if I plug in a 0, I could get 0 or I could get a 4. Did you catch that? Did you catch that? That 0 showed up twice in my domain that I could get 2 different answers for 0. No good. So the domain value of 0 has more than one range value. That doesn't work for functions. So that's not a function. D. Determine if this is a function. Is it a function? No, this relation is not a function. 4 is cool, 6 is cool, 8 is cool. Problem is that number 2 right there. Notice if you plug in a 2, you could get an answer of 7 or 20. No good. We said that for your inputs, for your domain, you should only get one output, one range value. Domain value of 2 is more than one range value, so it's not a function because you got greedy. It's not cool. What about our ordered pair here on part E? Negative 7, 5, negative 5, 5, 2, negative 2, 3, 5. Is it a function? Yes, it is. This relation is a function. Each domain only gave me one range value, so that's convenient. And last but not least, part F. Is it a function? Yeah. Yeah, this bad boy totally passes the vertical line test. This is a great chance to use the vertical line test where you just use a straight line, just a straight vertical line, just by touches once, touches once, touches once, touches once. Always touches once. It's only touching once. Yay. All right, we're going to bring it back to some stuff from the last lesson. So I hope you still have your graphs from the last lesson. Do you remember how on lesson 2, we cut out all those graphs and I was like, don't lose them because we're going to use them next time. But yeah, we're about to use them in just a little bit. If you even need to pause me and run off and go do that, that's totally fine. I got one more question here for you, and then we're going to play with those. Also, don't lose them today because you're going to need them for the next lesson. There's still one more. We're going to play with these. So, if you remember last lesson, Judy, right? Remember we were grouping together our graphs, and Judy grouped together graphs D, K, and O. These 3 graphs right here, D, K, O. Are the graphs she grouped functions? Tell me why or why not. Go ahead and hit pause, answer the question, and then hit play and we'll discuss it. So I'm looking at these bad boys and I'm saying, nah, they are not functions. Not one of them passes the vertical line test, right? If I were to draw a vertical line here, ooh, it hits twice. If I draw a vertical line here, it hits twice. And even this guy is a vertical line. So if I were to draw a vertical line on top of it, it would hit an infinite number of times. It's not good. So yeah, those are not functions. Those bad boys did not pass the vertical line test. It's very sad. So remember I just said that you're going to need all those graphs. So these are all the graphs. Remember in our last lesson, we had all these graphs. We had a whole bunch of graphs that you cut out and we were playing with them. We were doing all kinds of stuff with them. We're playing with them a little more today. And I should warn you, we're going to play with them a little more in the next lesson as well. So don't lose them. So what I'd like you to do is use the vertical line test. I love the vertical line test. If you even wanted to, you could get like a pen or something like that and just kind of like wave it back and forth over it. Make sure it only hits once, you know, whatever works for you. So use the vertical line test and you're going to sort all of these graphs, all right? And I want you to sort them into two groups, functions and non-functions, all right? So functions are going to go in one group and those that are not functions are going to go into another group. So here are all the lovely graphs. In case you've lost yours, don't lose them. And you can record your results by writing the letter of each graph in the appropriate column in the table below. So down below, you have this lovely table, and you can just write in there the letters of the graphs. You're not gluing them or anything today. You're just using them. Doesn't sound nice when I say it that way. So go ahead and sort your graphs into functions and non-functions. Hit pause to take care of that, and then hit play when you're ready to check your work. So I used the vertical line test on these bad boys, and I found out that functions, that graphs A, B, C, E, F, G, H, I, J, L, M, N, P, Q, R, and S were all functions. Hey. And then the ones that were not functions, D, K, and O. Thanks, Judy. Yeah. So yeah, my non-functions were D, K, and O. So let's talk a little bit more now about domain and range. You're going to want to, again, hang on to these graphs, especially that pile of graphs that are all functions. Hang on to those. You want those, okay? I'm just saying. As we move into the next activity, 3.2 on page M147. So you've identified domain and range of a function given its equation. I think you've done that in the past, like before this class, all that good stuff. But let's talk. There are different ways that you can identify the domain and range, all right? So you can do it using a verbal statement, all right? That your domain would be the possible values that make sense for your independent quantities. And your range is the possible values that make sense as the dependent quantities. So we've played with this a little bit before. I like finding, I mean, you can do it verbally, but you know what? I really like finding domain and range on a graph. That's probably my favorite way to do it. Because with my domain on a graph, I can just look for all the x values, right? On a graph, it's great. I'm just like, there are my x values. That's what my domain is. And that means on the range, for the range on a graph, I can just look at the y values. So it's really, really easy to do. And I'm gonna show you how easy it is. Are you ready to see how easy it is? I think I may need my little writing tablet here. Hang on. All right. So you're on page M147 at this point, and we've been playing with stuff up above, writing questions, all that good stuff. There's my pen. I have a pen. I'm gonna bust out the pen. Yeah. What color? Oh, we'll just go with red. I suppose there are other lovelier colors. We're just going to stick with this one for now. So if I come over here with my lovely writing tablet, my little red pen, let's look at this graph right here. So there are different ways to write the domain and range of a function given its graph. Now you'll notice it's hard to see here, easier to see in your book, but right here we've got a solid, oh, don't do that. We got a solid dot, and over here we have, no, don't do that. Okay, that was really bad. Over here we have an open circle. I know, this is really badly drawn. It's okay, just remember I love you guys, all right? So this is closed, this is open. That means that that's equal to and that's not equal to, so watch out. Now we said on a graph, for my domain, I can look at my x values. So how far to the left and how far to the right. So I notice for this first guy, it starts at -7 on the left, and it goes all the way up to 6 on the right. So I would say that the domain is all real numbers greater than or equal to -7 and less than 6. And because I'm a mathematician and I'm super lazy and I don't want to write The domain is all real numbers greater than -7 and less than 6. I am lazy, and I will write it like it is, as -7 is less than or equal to x is less than 6. This guy gets a squashed equal sign because his circle is closed. This one does not get a squashed equal sign because his circle is open. If we look at the domain on the other function though, so again, still looking at x values on my other graph, the issue is that on this other graph, there's arrows on either end. Remember that arrows means it goes forever and ever and ever and ever. So that means that there is no end on the left. It goes forever and ever and ever to the left. And there's no end on the right because there's an arrow over there too. So it goes forever and ever and ever to the right. So fine, I'm going to say my domain is the set of all real numbers because those arrows mean it goes forever to the left and forever to the right. Everything is possible for my domain. Because again, I'm lazy and sometimes I don't like to write. The domain is a set of all real numbers. I will write it like this. And I'll say, okay, all the way to the left forever and ever means negative infinity. And all the way to the right forever and ever means positive infinity. Please notice how I wrote it as negative infinity is less than x is less than infinity. There's no squashed equal signs underneath because you can't really equal infinity because there's no end. That's a thing. Let's do this again for the range. Yay! So we said derange. I am a little deranged by now. We said that the range was all possible y values. So let me take a look over here. There's my mouse. I knew I had a mouse here somewhere. Oh, nope, not what I wanted. Come on back. So my range is the y values. So how far down, how far up. On this first function, I can see it only goes as low as -2. That is the lowest it goes. And it goes all the way up to 8. Yep. And it's even equal to -2, and it's equal to 8 at different points. So I'm going to say that the range is all real numbers greater than or equal to -2 and less than or equal to 8. So greater than -2, less than 8. Again, math, I'm lazy. I don't want to write out the whole sentence, so I'll often write it like this. -2 is less than or equal to y, less than or equal to 8. So this just means that y is between -2 and 8. Notice we go lowest to highest. Notice how they both have squashed equal signs because that's closed at 8. And look, it's even closed down here at -2. Hey. H of x, let's look at the second graph. It's a little bit different, right? Because if you recall, it has those arrows. So it goes down forever and ever and ever. There is no bottom end. It has no bottom. Could get awkward. Maybe you don't have your bottoms on. I hope you do. Please have your bottoms on. That'll be a good thing. But it does have a top end, right? It has a top that it reaches and it doesn't go past it. So 8 is as high as it can possibly go. And it can go forever and ever below 8, but it never goes above 8. So I would say that the range is all real numbers less than or equal to 8, or y is less than or equal to 8. Because 8's as high as it goes, and it doesn't have a bottom. It never bottoms out. It just goes down forever and ever and ever. So with this in mind, here's what I want you to do. I want you to take the graph cards that included continuous functions. So remember how you separated your cards into like, these guys are functions, these guys were not functions. And remember how the continuous ones were the ones that like had actual lines and curves on them. It wasn't just dots. So I want you to grab your cards that you put into a pile for your functions. And I want you to just use the continuous ones. Don't use the ones with the little dots. Just use the ones with lines and curves that go forever and ever, that are all connected, all right? And what I would like you to do is on those cards, right, I want you to write on the card the domain and the range. And you can put it on the back if you need to. I know there's only so much space, but write on each of those little guys the domain and the range. Go ahead and hit pause. It may take you a few minutes to do that, and then hit play when you're ready to check your work. Now, I don't have cards in front of me because I'm on my computer, and so it's really awkward for me to like do the cards. So here's what I'm going to do. I'm going to just do the graphs in order, and you can just check to make sure that's the domain and the range that you wrote on your graphs. Sometimes I use words, sometimes I use intervals. It just depends on what I was doing. So graph A, I noticed it went forever and ever left to right and forever and ever up and down. So I said that graph A, the domain was all real numbers, the range was all real numbers. For graph B, I noticed it went forever and ever left and right, but not up and down. That it went as low as 2 and then it went up from there. So I said that the domain was all real numbers and the range is y is less than or equal to 2. For graph C, I said that the domain, again, is all real numbers, forever left, forever right. But that my range was y is greater than or equal to 0. For graph F, I said that the domain is all real numbers and the range was all real numbers forever and ever and ever. Graph G, my domain was all real numbers. My range was y is greater than 5. For graph H, my domain is all real numbers and my range is y is less than or equal to 0. For graph J, I said the domain was all real numbers and the range was y is greater than or equal to 0. For graph M, I said the domain was all real numbers and the range was y is greater than 0. For graph N, I said the domain is all real numbers and the range is y is less than or equal to 4. Graph P, my domain was all real numbers. My range was y is greater than or equal to -2. Graph Q, my domain is all real numbers and my range is y is greater than or equal to -4. And for graph S, last one, my domain was all real numbers and my range is y is greater than or equal to -2. All right, guys. I think that's it. I say that's it, but how long have we been on this video? A while, okay? So as always, guys, I hope you found this helpful and I hope you found this useful. If you got questions or concerns, let me know, email me, come see me during office hours, and I'll see you soon. Bye.